So in the previous video that I published, we talked about how we can write the electron configuration of an atom. And what that's going to do is that's going to describe where every electron is with respect to its shell and also the subshell. Now, what we'll find is that with 118 elements, once we get going after a little while, the number of electrons that the atoms have is quite a lot. So we're going to do something. We're going to write a condensed, or learn how to write a condensed electron configuration that makes the electron configuration a little easier to write and also to read and understand. The other thing that we're going to be doing in this video is looking at how electrons are organized in terms of orbitals. So we said that there are three ways of looking at where an electron is in space. There's the shell, there's the subshell, and there is the orbital. And to date, we haven't done anything about looking at what electrons are doing in orbitals. So it's important to realize that it is the outermost electrons of an atom, those that are in the highest shell, that are responsible for an atom's chemical properties, because it's through those electrons that an atom interacts with other atoms. Those electrons that are not in this highest shell, what we call the core electrons, they're going to be in completely filled up inner shells, and they don't contribute as much to an atom's chemical properties. They're not sensed as much by other atoms when two or more atoms come together. What we're going to do is we're going to write abbreviated electron configurations that put a shorthand representation of the core electrons in place, and then allows us to focus on the chemically important outer electrons in more detail. So I'll show you how this works. If we look at the electron configuration for potassium and calcium, we see that the first 18 electrons are all placed into completely filled subshells. So we completely fill the first shell in both cases, and then we fill the second shell completely, the 2s, 2p, and then we fill up the 3s subshell and the 3p subshell. They're completely full, and then we have the outermost shell in both cases is the 4s subshell. Okay, and then in the case of potassium, there's one electron in that 4s subshell, and in the case of calcium, there's two. So it's this last subshell here that distinguishes potassium from calcium. So in each case, the outer shell is in the 4th shell, and both of the atoms have completely full inner shells with the same number of electrons in them. So the inner shells, the core electrons, contain 18 electrons, just like argon. This configuration in here is exactly the same as the configuration that we see in the argon atom. So what we can do is we can write the condensed electron configuration for these atoms by substituting the symbol for argon in square brackets in place of the core electrons. So instead of writing out all of these 18 core electrons, we're just going to replace that with the symbol of argon in parentheses, and then we're just going to write the outer electrons after that. And we can do that for any atom that has 18 core electrons. Write the symbol of argon in parentheses, and then the chemically interesting outer electrons are written afterwards. So we can extend this to any element. It doesn't just have to be an element that has 18 core electrons. And what we're going to do is we're going to write the symbol of the preceding noble gas, that is the noble gas that comes before the element, in those square brackets, and then follow that up with the electrons needed to complete the atom. So sodium has 11 electrons. 10 of them have the neon configuration, and then there is the 1 electron in the 3s subshell. So we write its abbreviated electron or condensed electron configuration by writing the symbol for neon and then 3s1. So if you're wondering what element has to go here in parentheses, like I said, it's always going to be the noble gas that comes before. So the noble gases are over here: helium, neon, argon, xenon, krypton, radon, I think it goes. Okay, so that's how we're going to know what goes there. Again, magnesium has 12 electrons in total. The core electrons, the ones that are not in the outermost shell, are these guys. There's 10 of them, just like neon, and then these are the interesting outermost electrons. Boron has 2 core electrons, the same as helium. We always know how many core electrons we're going to have because we look at the preceding noble gas, and the noble gas that comes before boron is helium. Similarly with oxygen, oxygen is element number 8, and the noble gas that comes before it is helium. Helium has 2 electrons, so we know those are our core electrons, and we can replace them with the symbol for helium. And then these guys are our chemically interesting outer electrons. So that kind of deals with the first topic that we were going to cover in this video, in that we've come up with an abbreviated or condensed manner for writing in the electron configuration of an atom that focuses on the chemically interesting electrons. Now we move on to the second topic, which is where we're going to start investigating how electrons within a subshell are organized into orbitals. So the important thing to recognize is that an S subshell has 1 orbital. A p subshell has 3 orbitals. A d subshell, 5 orbitals. And an f subshell has 7 orbitals. S orbitals are spherical. The p orbitals, they're these kind of 2 teardrop-shaped lobes. The d orbitals, most commonly they're kind of like clover-leafed in shape. And then the f orbitals are really complicated, and they have many lobes, as many as 8 or more. The question becomes, though, how do we describe how electrons are arranged in orbitals? What are we going to do? We don't get that from an electron configuration. An electron configuration just tells you the shell and the subshell. So we use this thing called an orbital diagram to describe how electrons are arranged in orbitals. So we have to keep in mind 2 principles when we're placing electrons into orbitals. The first is the Aufbau principle, which we talked about before. We're going to put electrons into lower energy orbitals first before we put them into higher energy orbitals. And then the second rule that we're going to be using is this rule called Hund's rule, and that's going to allow us to make certain that we assign electrons with the correct spin into these orbitals. And you'll see how Hund's rule comes into play in a moment. So we will need to know how to use an Aufbau diagram in order to place electrons into orbitals with the in the correct energy with respect to in the correct order with respect to energy. So as I mentioned before, we want to keep in mind that an S subshell has 1 orbital, a P subshell has 3 orbitals, a D subshell has 5 orbitals, and an F subshell 7. So this is Hund's rule, and what Hund's rule states is this, that electrons will not join electrons in the same orbital if an unoccupied orbital of the same energy is available. If we do put electrons into the same orbital, then they will have opposite spins. So what we really mean is if we're to consider a p subshell, could be any p subshell, could be the 2p, could be the 3p, whatever, it doesn't matter. That subshell will be made out of three orbitals, which we indicate normally by either 3 lines or 3 boxes. Either or, whatever feels more comfortable. And if I wanted to put in 3 electrons in there, then according to Hund's rule, what I'm going to do is I'm going to put 1 electron into each orbital by itself, first of all. What I'm not going to do, even though I know that an orbital can accommodate up to 2 electrons, I'm not going to pair up and leave 1 empty. If I do have an orbital available, I'm going to fill that guy up before I start pairing electrons up. So it's kind of like seats on a public bus, right? You know, you're not going to choose to sit next to a stranger if there's an empty available seat. Okay, so that's how that kind of works, you know, or children with bedrooms in a house, you know, parents get married, they decide they're going to have 2 kids, they buy a 3-bedroom house. First baby comes along, gets its own room. Second baby comes along, gets its own room, because you don't want to put kids together, they'll fight. And then, you know, 5 years later, whoopsie, an accidental 3rd baby comes along. Guess what, kiddo? You have to share, right? So you don't start sharing until you have to. Now, by convention, we always place the first electron in an orbital with its spin being up, and we indicate an electron with a half-headed arrow. The second electron always goes in with the spin down. So now we have the information that we need to be able to place electrons within an orbital and then illustrate that as well. So in an orbital diagram, electrons are indicated by upwards or downwards directed arrows. Orbitals normally indicated by boxes. Some people will do circles. A lot of people will do lines, but what is important is that they do need to be clearly labeled as to what the subshell is that they're depicting with the diagram. And so we'll do a couple of periods of this like we did for electron configurations. So we'll begin with hydrogen. Hydrogen has atomic number 1, so that means it has 1 electron. So its electron configuration is 1s1. So you want to be aware of that. That's the electron configuration, not the orbital diagram. And then the orbital diagram looks like this. I've put a box here to represent the orbital. I've labeled it 1s, and then it's got 1 electron, so that goes in as a half-headed arrow upwards. Now, when you have 1 electron in an orbital by itself, that electron is described as being an unpaired electron. Okay. So helium has 2 electrons. Its electron configuration is 1s2. So in the orbital diagram, we're going to 1s. There's 1 orbital for a s-type subshell. So we put 2 electrons in there. 1 would spin up, 1 would spin down. And when we have 2 electrons in the same orbital, we describe those electrons as being paired. So that completes period 1. So now we're on to period 2, which is lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. And so we'll work through here. So lithium's got 3 electrons. Electron configuration is 1s2, 2s1. Now, something to recognize here is that anything other than the outermost shell will always be completely filled up, and you can kind of see that here. So we've got 1s2, 1 goes in with the spin up, the next one goes in spin down, then 2s1, and by convention that electron goes in there spin up. Okay, so on to beryllium. Beryllium has got 4 electrons, so we can write the electron configuration a couple of ways. We can write 1s2, 2s2, or we can do the condensed electron configuration and write helium 2s2 if we wanted to. So here's our 1s2 core electrons and then 2s2 outer electrons. Now, an atom that has no unpaired electrons, it has a special name. That kind of atom is described as being diamagnetic. Okay, so we've defined a few terms along the way. We have a paired electron, unpaired electron, and then now we've described an atom as being diamagnetic. Okay, so boron, 5 electrons, 1s2, 2s2, 2p1. The core electrons are from the preceding noble gas, which is helium, and then 2s2, 2p1, they're our outer electrons. So here we go, 1s2, 2s2, 2p1, and remember we have to apply Hund's rule from here on in. The next 2 electrons will go in spin up into their own orbitals, and then we're going to start going spin down. Okay. So keep that in mind. So this atom here is not diamagnetic, right? It's not diamagnetic. Maybe there's a special term other than not diamagnetic. We'll see in a moment. Okay, so now we're in carbon, element number 6. So it's got 6 electrons, 1s2, 2p2. So 1s2, 2s2, 2p2. See, the second electron goes in by itself. So we always put them in, the unpaired electrons in by themselves, spin up. They always go in, all of them go in, spin up, and then the second one all go in, spin down. So nitrogen, 7 electrons, 1s2, 2s2, 2p3. So 1s2, 2s2, 2p3, there's the third one. So here's another little bit of another little definition here, another little bit of vocab. Atoms that have 1 or more unpaired electrons, and this guy has 3 unpaired electrons. And this guy has 2 unpaired electrons. Atoms that have any unpaired electrons are described as being paramagnetic. So paramagnetic is kind of the opposite to diamagnetic, right? So diamagnetic has no unpaired electrons. Paramagnetic has 1 or more unpaired electrons. And you can get quite a few unpaired electrons. Okay. Oxygen, 8 electrons, 1s2, 2s2, 2p4. Helium is the preceding noble gas, has 2 core electrons, and then these guys here are my outer electrons. So it's 1s2, 2s2, 2p4. You can see when I put that fourth one in, it goes into the first orbital there, spin down. Fluorine, it's got 9 electrons, 1s2, 2s2, 2p5. Helium is the preceding noble gas. So helium there, 2 core electrons. And then these guys are the chemically interesting outer electrons. So we've got 1s2, 2s2, 2p5, and you see now we've put in another going in here, that fifth p electron goes into an orbital with another electron, and so now we only have 1 unpaired electron, so still paramagnetic. Okay, and then finally we get to neon at the end of period 2, atomic number 10, so it's got 10 electrons, 1s2, 2s2, 2p6. Preceding noble gas is helium, so 2s2, 2p6, so these would be considered the outer electrons, these would be the core electrons. Now, it's kind of a weird thing, right, writing a condensed electron configuration for a noble gas, but remember our rule was we write the preceding noble gas represents the core electrons, 2 electrons, and then these are the outer electrons, and then there's 8 electrons in the outer electrons. Okay, so now I've got 1s2, 2s2, and then 2p6. So the 2p subshell is completely full up. So we know now that according to our Aufbau diagram, if we were to go on to the next element, which is sodium, so sodium has atomic number 11, and then that would have electron configuration 1s2, 2s2, 2p6, 3s1. Neon is the noble gas that comes before sodium, so the neon would represent the 10 core electrons, and then the 3s1 would be written for the outer electron. Okay. Now, if I was to write an orbital diagram for this, I would need 1, 2, 3, 4 subshells. So we've got the 1s1, the 2s, the 2p, and the 3s. Now, I'll give you a little hint that you only see unpaired electrons in the outermost subshell. So without thinking, I just pair everything up in here, because that's full. And then I just have to think, okay, I just want the 1 in that guy. So anything other than the outermost shell is going to be completely filled up. The core electrons are in completely full orbitals. All right, so this kind of gets a little interesting. If I look at the electron configuration for all of the elements that are in the same group, and in this case I've listed this out for group 1A, what do you notice? When you look at those chemically interesting outer electrons, you see something. And what you see is this. You see that the highest shell in every case is equal to the period number. Lithium is in period 2, and its highest shell is 2. Potassium is in period 4, and sure enough, its highest shell is 4. Francium is in period 7, and its highest shell is 7. So that's kind of interesting, right? So at least for the representative elements, the A group elements, the period number corresponds to the highest shell that is occupied. Now, let's have a look at the electrons that are in that outermost subshell. And in every case, it's the same. In every case, the last electron for all of the elements that are in group 1A is always a single electron in an S-type subshell. So these guys all look the same, right? Because remember that S subshells are all kind of spherical. So the last chemically interesting electron in every case here is in the same type of subshell. So they look all, their outer surfaces all look kind of similar, right? So it's not surprising that all of the elements in this group behave chemically in a similar kind of manner. And we're going to see that for all of the groups, especially for the representative elements, that the outer electrons are in the same type of subshell every time, and also that the highest shell corresponds to the period number every time. So that's kind of interesting. What this means is that elements that are in the same group behave chemically similar because their outer surfaces are similar, and it's through their outer surfaces that atoms interact with one another. So let's have a look. This is for group 5A. Okay, and so nitrogen is in period 2, and sure enough, its outermost shell is the second shell, and it has a total of 2 plus 3, 5 electrons. If I go to arsenic, arsenic has is in period 4, and sure enough, its highest shell, here it is, 4s2, 4p3, is the fourth shell, and it's got 2 plus 3 electrons, that's 5 electrons in that fourth shell. So 5 electrons in the fourth shell, and sure enough, it's in group 5A. Now, you have to be a little bit careful to recognize that the 3d10 is not part of the fourth shell. So you do have to make certain that you add up the all of the electrons that are in the outermost shell, even if they are in a kind of disjointed order. Okay, so here we have this again. Here we've got antimony. What you don't want to do is forget that there are these 5s2 electrons in the in that fifth shell there. So antimony is in period 5. Its outermost shell is the fifth shell. It has 5 electrons in that fifth shell, and it is in group 5a. So what you'll notice is that the total number of electrons in the outermost shell always equals the group number for an A group element, for those elements that are called the representative or the main group elements. Okay. So there seems to be a relationship between the position of an element in the periodic table and its electron configuration. And when you look at the periodic table, which was constructed by by categorizing or placing elements on the basis of their physical and chemical properties, not at all thinking about electron configurations, we notice some interesting things. On the far left, there are 2 groups that kind of are sitting a little taller than the main region of the periodic table. 2 groups, okay? In the middle of the periodic table, sitting a little lower than the ends of the periodic table, there are 10 groups. 10 groups. And then on the right of the periodic table, sitting a little higher than the central block, there are 6 groups. 6 groups. Interesting. And then underneath the periodic table, in these 2 rows that go are these inner transition elements, we see, what do we see? 14 columns here, 14. So where have we seen these numbers before? 2, 6, 10, 14. Well, 2 is the number of electrons that you can put in an S subshell. 6 is the number of electrons that you can put in a P subshell. 10 is the number of electrons that you can put in a D-type subshell, and you guessed it, 14 is the number of electrons that you can put in an F subshell. So the periodic table can be divided into S, P, D, and F areas, or sometimes they call them blocks of the periodic table. And we can always figure out that what the outermost electron's subshell type will be on the basis of where an electron is, where an atom is in the periodic table. So for example, anything that's over in these 2 groups on the far left is going to have its outermost electrons in an S-type subshell. Anything that's in the middle of the periodic table is going to have its outermost electrons in a D-type subshell. Anything over on the far right is going to have its outermost electrons in a P-type subshell. And underneath, of course, you guessed it, its outermost electrons are going to be in an F-type subshell. So we often think of the periodic table, as I said, as being divided into blocks or areas. Because we've got these group numbers and we've got these period numbers, we can actually go kind of one better in identifying what that last electron is going to be. Because we know that the period number tells you the highest shell, and the group number tells you the number of outer electrons. Right? So I know that this element here, and we'll have to do a little bit of explanation here. If you see how this periodic table is labeled, this element here, its electron configuration is going to end 4s1, 4s2, so 4s2, and then it goes 3d, 1, 2, 3, 4, 5, 6, 7. 3d7. So I always know the outer electron configuration, and then if I wanted to write the rest of its abbreviated electron configuration, all I would have to do is identify what was the noble gas that came before, and it goes helium, neon, argon. So for this element here, its preceding noble gas would be argon. And so I can write the condensed electron configuration very quickly, right, using a periodic table that is, and thinking about the different blocks of the periodic table. So let's do another one. If I wanted to write the electron configuration for this element here, I would write the name of the, or the symbol of the preceding noble gas in square brackets. And then I would say, okay, so this is 2s, 2s1, 2s2, and then this is 2p, 2p1, 2p2, 2p3, 2p4. And I could check whether I was right, because this guy should have a total of 6 outer electrons. So 2 plus 4 equals 6. Its outer shell is 2, and its period is 2. So very, very quickly I can get the condensed or abbreviated electron configuration, and when I think about a periodic table as being divided into S, P, and D blocks. Now I want to just point out two little things. For the S block, you can see if I let the period number, we often label that as, or call that the shell number, N, right? You can see that the subshell corresponding to a particular period is just simply what we call NS, isn't it? Right? Whatever the period number is, then you can just follow that up with the S. Now for the D block, it's a little weirder, right? You see here period 4, but this row across here, we're putting electrons into the 3D subshell. So people will often label this N-1D. Okay? Now, following along period 2 again, when we get over to the P block, you can see that this is putting electrons into the 2P subshell. So people will often say, so the 2 is the same, the N is the same, so people will often label this NP. Now this gets a little weird. When we're in N equals 6, period 6, you can see that the F subshell that we're filling up as we move across here is the 4F, so it's 2 behind. So people often label that N-2F. So you'll see people label periodic tables like this. For you guys, you want to hang on to that, keep that in the back of your mind. You're probably going to be doing a non-online chemistry class at some point. But for now, what you should be able to do is, given a periodic table, and you can label it any way you want, or you can find it on the internet, and you can get this ready beforehand, you should be able to fairly quickly, by looking at what block your element is in, and what group number it has, and what period number it has, you should be able to write the condensed electron configuration in, sort of like, 10 seconds or so. Okay? All right. So the key idea here is that you can always figure out where that last electron is, right? The one, the one that's at the very end of the electron configuration, just by looking at what region of the periodic table it's in and then counting off. Okay, so a lot of people will print out a periodic table that looks like this, and will use this as an alternative, or in addition to the Aufbau diagram, in order to count off an electron configuration from the periodic table. So it goes 1s1, 1s2, 2s1, 2s2, 2p1, 2p2, 2p3, 2p4, and so forth. And you can count off an electron configuration like that. Now this is a lot harder to kind of draw if you don't have it in front of you for a test, and that's why the Aufbau diagram is popular, because that's very easy to draw. Okay, we're going to talk about another property, or another way of labeling electrons. We're going to talk about valence electrons and non-valence electrons, or valence electrons, and we've already heard of these, what we call core electrons. So for the representative elements, those that have an A in their group number, or a noble gas, which is 8A, so a valence electron is defined as an electron in the outermost shell. So these are always going to be those that are in the outermost S and P subshells. Now, transition elements, those that are in the D area of the periodic table, in their valence electrons, we have the guys that we've already defined, those that are in the outermost shell, plus any that are in a partly filled D subshell. And this doesn't come up very often, but I'm just mentioning it now for completeness. Now, this sounds like kind of a lot, but it's a pretty easy concept to get hold of. Now, there's a really cool system developed by an American chemist called Gilbert Lewis. And it's a pictorial system that illustrates the number of valence electrons that an element has. And it's super simple, and it makes things very, very clear in comparison to always using an electron configuration. So what we do is we write the Lewis symbol of an element by placing dots equal to the number of valence electrons around the symbol. And remember, the number of valence electrons that a representative element has is just equal to its group number. So it's real easy. Okay. Now, all we do is this though. If I'm just going to pick one like tin. Tin is in group 4A, so I know that it's going to have 4 dots. It doesn't matter where you start, top, bottom, left, or right. But what you do is you just put 1 dot at each of the compass points. And it doesn't matter whether you go clockwise or anti-clockwise, okay? Now, say that we want to do something that has more than 4 valence electrons. Let's do oxygen. It has 6 valence electrons. I'm going to go 1, 2, 3, 4. And then I start doubling up at each of the points, okay? And again, it doesn't matter left, right, top, bottom, what comes first. And it doesn't matter whether I go anti-clockwise or clockwise around the atom, adding dots. Because sometimes we want our unpaired dots in a particular position, and then other times we want them in another position just because we care about how our diagram looks. So it doesn't matter. The key thing is that for a representative element, your number of valence electrons and hence your number of dots is always equal to the group number. So it's super easy to do this. Okay, so that concludes section 2.8 on the electronic structure of atoms. By electronic structure, we just simply mean how are the electrons organized into shells, subshells, and orbitals. And we've done a pretty good job of covering that.